Now we start with an open convex subset of a non-empty of Rp. Now we assume that the second order partial derivatives of f are, well, all exist and are continuous on U. Now, F is concave, respectively convex, if and only if the Hessian of f at A is negative semi-definite respectively positive semi-definite at each A in U. Now for the strict version, well, we have just a one directional statement. It's not a biconditional. If H sub Fa is negative definite, respectively positive definite, at each A in U, then F is, in the first case, strictly concave, and in the second case, strictly convex. Now we also have seen a simple example which shows the converse is not true, okay? So let's start with the proof of this. Now let's wait for the concave case that will automatically lead to the proof of the convex case, and well, these will be obtained actually easily from what you have for the semi-definite case. So let's first start with the if part. Assume that the Hessian of f at A is negative semi-definite for each A in U. Now, in showing that f is concave, we will use the characterization of concavity in terms of the first order, in terms of the first derivative of f. Now for that, let us first take any uv in U. Well, since U is convex, this segment uv is in U since U is convex. We also had noted last time that the Hessian, well, that's closely related to the second derivative of f at a. In fact, the second derivative of f at a evaluated at x, that could be written as x h sub f of a, the Hessian, times x transpose when x is considered as a row matrix. Well, then here, since this is in U, this is open, and on U we have all the second partial derivatives, second order partial derivatives continuous. So this means Taylor's theorems, hypotheses are all satisfied for n equal to 2. Note that the hypotheses in Taylor's theorem are all satisfied for n equal to 2. Well, then we can write f of v in terms of f of u and its derivatives. So there is some u bar in this segment, uv, such that we have f of v is equal to f of u plus, well, 1 over 1 factorial, but we don't write that, dfu at v minus u plus 1 over 2 factorial, that's 1 over 2, the second f at a, no, at u bar, and here we have v minus u comma v minus u. This stands as an abbreviation for that. Okay? But now what do we know? Okay. Now the second f u bar evaluated at v minus u, v minus u. This we know is v minus u the Hessian at u times v minus u transpose. What can we tell about this? Since we know that h sub f at any point in u, thus in particular at u bar, this is negative semi-definite. Well, so if x is v minus u, this is less than or equal to 0, since h sub f at u bar is negative semi-definite by hypothesis. But then, if, well, 1/2 times that, that's less than or equal to 0 as well. So, if we rewrite it like this, f of v minus f of u minus this, well, that will be less than or equal to 0. So, this means that we have df of u v minus u. But u and v were arbitrary, so this for any uv UV in cap U. But this was equivalent, F being concave in case F is differentiable. Here it's differentiable. In fact, it has also the second derivative. Thus, F is concave. Okay? Well, using Taylor's theorem and having this expression also seems to be promising to prove the converse. Because this is an if and only if statement. Well, if F is concave, this will hold. And this time that will imply that for this particular U bar, which depends upon U and V, thus this Hessian, that will be less than or equal to 0. But here we have an additional difficulty. We have no full control on U bar. We need to show that H sub F of A, that is negative semidefinite at any A in U. Well, can we get any A in U such that it is U bar for some UV? So that's the question. If we start with any UV, well, there is some U bar in the segment, but it might be the case that you might have some A in U, no matter what UV you take, which contains such that the segment UV contains A. Well, that might never be U bar corresponding to those UVs. But now we can deal with that as follows, but let us first start with the converse. Conversely, assume that F is concave. Now, what do we need to show? For any A in U and for any X in RP, X times the Hessian matrix of F at A times the transpose of X, that should be less than or equal to 0. So let's take any A and any X. Now take any A in U and X in RP. Now we want to show that X, the Hessian, X transpose is less than or equal to 0. The way we will deal with that is we will construct a sequence of segments UMVM such that each of them contains A, but then for each M, when we apply Taylor's theorem, there will be some U bar sub M which does the job. But if UM and VM come closer and converge to each other, well, the U bar M's, well, since it's a complete space, RP, they will converge to something, but A is always in between, so there is no other point than A to which they will converge. Okay, so let's try to do that. Okay, so, well, first, since U is open and A is in U, There is some epsilon ball about A, which is entirely contained in U. B epsilon A, that will be contained in U for some epsilon positive. So this is A. Now we have the epsilon ball about A. And also we have this X. Now I can actually find some for each M, UM, VM. Well, but I have to adjust this in such a way that as M gets larger, they come closer to each other, UM and VM. Moreover, that has to be related, since eventually we wish to show this. It has to be related to cap X. Now, first, when X is equal to 0, which is possible, X, HFA, X transpose, that will be 0, no matter what HFA is. So we can assume that X is different than 0. We have the proof for X equal to 0. Now, assume that X is different than 0. Now, for each M in N, set UM equal to A minus this epsilon over M times the norm of X times X, and VM equal to A plus epsilon over M times the norm of X times X. So I take this in the direction of X, this line segment. Well, X is different than 0, so this will be positive. This will be well defined. Okay? Now, for each M, UM minus A, the norm of that. Well, I'll get the norm of this, but the norm of X divided by this, they will get canceled. This will be equal to epsilon over M. That will be less than epsilon. And VM minus A, well, again, that will be epsilon over M, and that will be less than epsilon for each M in N. So that both UM and VM, they belong to the epsilon ball about A, but that's in U. So they will be both in U. UM, VM is contained in U. Now this time, all the hypotheses of Taylor's theorem will hold for UM, VM, and when N is equal to 2 again. Because this is just the common assumption about proceeding this biconditional. The hypotheses of Taylor's theorem hold for N equal to 2 and UM, VM for all m in n. Well, thus, again, for each m in n, there's some u bar sub m in here. Such that f of Vm is equal to f of Um plus df at Um evaluated at Vm minus Um, and then plus 1/2 the second derivative of f at u bar m Vm minus comma Vm minus but that's this. Okay? Now we can use the concavity of the function f. Thus, for each m, we have that f of Vm minus f of Um is less than or equal to this derivative. Since f is concave and is also differentiable, concave and differentiable on u, we have that f of Vm minus f of is less than or equal to df at Vm minus for each But that simply means for each m again that this is less than or equal to 0. Thus, for each m in n, well, let me also write this. That is equal to Vm minus the Hessian at bar times Vm minus the transpose of this. That is equal to the second f at bar Vm minus transpose. This is less than or equal to 0. Now, what's Vm minus Well, the a's get cancelled, and you'll have twice this. Okay? As Vm minus is equal to 2 epsilon over m, the norm of x times x. We get that this now 2 epsilon m, the norm of x, which is just a real number, x, is times h sub f u bar m, and then here we have 2 epsilon m over x, x transpose is less than or equal to 0. But since these are positive scalars, well, I can divide by them on both sides so that we get just x hf um bar x transpose is less than or equal to 0, and all this for all m in n. Now we are almost there, but by construction, A is the midpoint of each of these segments, and U bar M, that's in here. So, well, it's straightforward. I will leave checking that M bar converges to A. Okay? For each M, A is the midpoint, and M bar is somewhere. But if you make this smaller, well, M plus 1 bar, that's in here, but A is the midpoint again, so it's easily seen, or check that. M bar converges to A by construction of Bm for each M in N. Now we have this, well, x is given, it's arbitrary, but we keep that fixed. So keep that x fixed, so this becomes a function of the argument of h sub f. Is that a continuous function? That is the function. Well, now the function which sends each u in u to x h sub f u x transpose. Well, that's a function on u with real values. Is this a continuous function of u? Well, here the arguments of this matrix, they're the second order derivatives of f with respect to different variables, but by hypothesis, all of them are continuous. So you have here p-squared continuous functions, and if you perform this matrix product, well, you will have just a combination of those. Since scalar multiplication and vector addition, they are both continuous, this will be continuous. Is continuous since the entries of h sub f of u are all continuous by hypothesis, and since scalar multiplication and vector addition are both continuous in Rp. Now, what's the use of this? We have this for each n. So, does this converge to something? Well, it's a function of u, but um bar, that's a convergence sequence. It converges to A. So the value of this function, well, that converges to x h sub f of A, xt. Thus, the function x hf u bar n x transpose, this now is a function in R, because each term is in R, this converges to x h sub f of A xt. But since this is less than or equal to 0 for all n, well, this inequality holds in the limit as well. Moreover, x hf A x transpose is less than or equal to 0, since for all m in n, x hf um bar x transpose is less than or equal to 0. But then, since A was arbitrary in U, X was arbitrary in Rp, this means that the Hessian matrix is negative semi-definite at each point in U. So, H sub f of A is negative semi-definite for each A in U, completing the proof. Okay? Now we have all the 5 characterizations that we promised. But at the end of each section, well, we said we will summarize what we have learned about optimization by that section. Now let's do that. Now remember, at the end of the last section, well, we had, well, in case f is a nice function, x star is in its domain, f of x star is equal to the supremum of f of the domain, well then f sub u of x star, in case it existed, the directional derivative, that was less than or equal to 0, and if the function was differentiable and the point x star was an interior point of the domain, well then the derivative was equal at that point x star was equal to the 0 function. But we have seen, and we know from calculus very well, that the converse is not true. But here we have a partial converse for maximization if f is concave, and for minimization if the function f is convex. So let's have that. Now I'll start with the non-empty subset S of Rp be convex, and f on S to R. Now, in the first case, a concave function. In the second case, a convex function. Now, furthermore, assume that x star in S is a cluster point of S. Moreover, assume that the directional derivative of x star in the direction of u exists whenever u is a vector which points into S at x star. Otherwise, the directional derivative will not be defined at all. Exists for each u in Rp pointing into S at x star. Now, if f sub u of x star is less than or equal to 0, respectively, f sub u of x star is larger than or equal to 0, for all u in Rp which point into S at x star, then f of x star is equal to the supremum of f of s, that's the maximum of f of s, because this means that f of x star is in this set, x star is in S, and here f of x star is equal to the infimum of f of s. Well, this also automatically implies if x star is differentiable at x star and x star is an interior point of S, then the derivative at x star, that being equal to the 0 function, for a concave function, it will imply this. Every u points into S if x star is an interior point. Well, if f sub u of x star is 0 for each u, well, then it's less than or equal to 0. If you combine that with concavity, then f of x star will be this, and otherwise will be this. Now let me write that as a corollary. Then we'll prove this. So we have this part again. Now we assume that x star is, well, x star is an interior point of S, and f is differentiable at x star. Now, if df of x star is equal to 0, then in the black case, that is when f is a concave function, f of x star is equal to the supremum of f of s. And in the red case, when f is a convex function, f of x star is equal to infimum of f of s. This is a straightforward corollary to this. So here again, this is of course much more powerful than this, and it is just when you use differentiation, well, if you're at the climax, when you move away from that in an admissible direction, you must be going downwards, downsloping. But this says, well, if that's the case, if no matter in which direction you move away from x star, so long as you stay within the set, within the domain of the function, by doing so, that's what you pointing into S means. Well, if you always go downward, if it's always downsloping in each admissible direction, then that must correspond to a maximum. Okay? In case the function is concave, so that's what the concavity does. Now let's prove this. Now the proof will be not long and not difficult, but it's again telling about the trick we have been using before and we will keep using in the sequel when we consider concave convex functions. Now proof. Well, let's assume this, that f sub u of x star is less than or equal to 0 for all u which point into s at x star. Assume that f sub u of x star is less than or equal to 0 for each u in Rp pointing into S at x star. Now suppose f of x star is not the supremum of f of s. Well, this means what? Well, there is some z in S such that f of z is larger than f of x star. Then there is some z in S with f of z larger than f of x star. Well, then the most natural thing to do is to check what happens when you go away from x star but towards set. So set, now well, it means since here you're at a higher point, well, it cannot be the case that you will be going downwards all the time. But it is possible first to go downward and then go up. That will not be possible since the function is concave. If the function is not concave, that might happen. Set u equal to z minus x star. Well, let's stop at this point, have a break, and then continue next hour. Well, the first thing is to check whether this u points into a set x star. Well, then there should exist some delta such that the segment from x star to x star plus delta u, that should stay entirely within S. But now, if you start with x star and have here x star plus 1 times u, delta, you take delta as 1, this will be x star, and 1 times u, that's z minus x star. You'll get z here, but that's in u since u is convex. Because both x star and z are points of S. So, u points into S at x star. And if I take any t in the interval 0, 1, but let me leave out 0 for what I'll say now, 0 included, that's also true, that will also be valid. X star plus tu, that will be in S. No, this is S, not U. This time we said the domain was S this time, okay? Now, what do we know? Well, we know that F is concave. So now, for each t in 0, 1, let us consider f of x star plus tu. Because the directional derivative of f at x star in the direction of u will be this expression minus f of x star divided by t, and you take the limit as t tends to 0. But this is equal to f of x star plus t z minus x star. But this is nothing but f of 1 minus t x star plus tz. So the argument is a convex combination of x star and z. T is positive and these add up to 1. So this is larger than or equal to 1 minus t f of x star plus t times f of z, this since f is concave. Okay, but now I can take this 1 times f of x star, subtracting it, here I'll get f of x star plus tu minus f of x star, which I wish to have. So f of x star plus tu minus f of x star, that will be larger than or equal to, and here I will be left with t times f of z minus f of x star. But I can divide by t when t is in this interval, is positive. 1 over t will be larger than or equal to this for any t in 0, 1. But what do we know about the directional derivative of x star at u? By hypothesis it exists, because u points into s at x star. Now by hypothesis, f sub u of x star exists, and thus limit 1 over t f of x star plus tu minus f of x star, t tending to 0. This is equal to f sub u of x star, but this is larger than or equal to 0. Well, larger than or equal to this f of z minus f of x star, which is positive, since f of z was supposed to be larger than f of x star, but that's a contradiction, because f sub u of x star in this particular direction, contradicting that, f sub u of x star was less than or equal to 0. Well, the convex version is similar, just take the negatives of everything, so you get this result.